We return to the task of image denoising, and now we introduce patch-based algorithms.
And the core idea is this. We understand that bringing in SparseLand to the denoising task will necessarily pass through the P0 epsilon problem. And in this formulation, the dictionary is of central importance. The approach we took so far was a global modeling, and since we do not know how to train a dictionary for such a case, we compromised and chose a specific wavelet. In order to be able to train the dictionary, we must turn to operate on small image patches, imposing our model on them directly. There are many benefits to this approach of working with patches beyond the ability of using a learned dictionary. We can use simple pursuit algorithms. We can parallelize the processing because each patch is treated independently. The annoying issue of getting dense representations will vanish. And beyond all these, this will give us the freedom to operate on images of any size. Next to these benefits, we have to be fair and mention possible problems. The one that should immediately pop to your minds is the suboptimality of such an algorithm. After all, a model should refer to the whole image, so could we theoretically justify such an approach? Let's start with a simple patch-based method inspired by the brilliant work of Onur Guleriuz. Given the noisy image, divide it into non-overlapping patches. For each of these patches, approximate the P0 epsilon and then put the cleaned outcomes back to their location. So, here is a patch to be processed. You approximate a sparse representation for it, multiply by d, and put it back to its location. In order to complete this description, we need to decide on d, epsilon, and the algorithm to use for approximating P0 epsilon. So here are the choices that we make. We will use the unitary 2D DCT as our dictionary. Epsilon will be simply the noise level in each patch. And the approximation will not be an approximation, but rather an exact solver since D is unitary. We will use the thresholding algorithm. This is our scheme, and all its steps are now well defined. Notice that in the thresholding, the threshold T will be chosen for each patch differently so as to allow a fixed epsilon deviation. And here are the results. The patch size was chosen to be 16 by 16 pixels, the noise level is 20 as before, and the outcome leads to 26.5 dB, which is even worse than what we got before. Zooming in, we see immediately why. We get strong blockiness artifacts. In fact, I'll take the risk and add another statement that might confuse you. We are lacking an averaging effect of some sort. Observe how each patch chooses its own atoms and gets crazy approximation of its content. These patches must speak with each other, but how? Let's improve the above scheme in two very simple steps. The core treatment of each patch will remain as suggested, but we will improve the overall performance by operating on fully overlapping patches and averaging the results. Later on, we could consider using a redundant dictionary instead of the unitary one, and even consider learning it. This idea of operating on overlaps appeared already in a paper from 1995 by Koifman and Donahoe as the core concept behind the method they called cycle spinning. Guleriuz perfected this in 2007 by suggesting a smart weighting over the overlaps. So let's experiment with this. We stay with the unitary dictionary but allow overlaps. A key question is the matter of the size of the patch to use. Note that if the patch size is n by n, then every pixel is covered by n squared patches, and these values will be averaged. Thus, on one hand, when the patch is big, a stronger averaging effect takes place, and perhaps this is beneficial for our result. On the other hand, as the patch grows, the model becomes less and less accurate. Also, overlapping patches may tend to disagree, and then we will get blurred outcome. Thus, there is an optimal value that needs to be identified, and we will find it by simply trying. Look at these two curves, showing the PKSNR as a function of the patch size n. With no overlaps, the performance is poor and stands on 26 dB at best. With the overlaps, the best performance achieved is 30.55 dB obtained for n equals 21. This is a much better result than anything we have seen so far. Look at the resulting image. It looks really good. Zooming in again, we see almost no trace of those artifacts we saw before. So could we do better? Let's see.